Hi class, this video was on topic C8, nuclear fission, fusion, and CANDU reactors. And this is actually the last lesson of our energy unit. So we're talking about fission and fusion. So recall that nuclear energy is stored energy that can be released by a nuclear reaction, and that a nuclear reaction unleashes the energy deep within the nucleus. There are different ways to release the nuclear energy through naturally occurring radioactive decay, which we talked about in the last video, or through nuclear fission, which we're going to talk about a lot today, and nuclear fusion, which we're going to talk about a little bit today. So here's a good graphic for just seeing the visual difference between fusion. So fusion means to split. So the atom splits into fragments, into two or more fragments. And then fusion means to join. So when a larger nucleus is more likely to split, to undergo fission, and smaller nuclei are more likely to fuse or to undergo nuclear fusion. So nuclear fission occurs when a large, unstable nucleus breaks apart into smaller, more stable nuclei. And fission means to split. The binding energy of a nucleus is released and converted to a useful form of energy. Binding energy of the nucleus is released. So neutrons, fast-moving neutrons start this reaction. And neutrons are also, high energy neutrons are also released in this reaction. And then they are free to cause further fission with the fragments that are left that are still relatively large. So what really is this binding energy that is released? So the binding energy is the amount of energy that we would need to supply in order to break apart the nucleus into the protons and neutrons that are making up this atom. So writing this in sort of a form of a visual equation, we supply energy to the atom to break it up into its nucleon fragments. Or sorry, not fragments, but the individual protons and neutrons. So we call protons and neutrons nucleons. According to the law of conservation of mass, the mass before should equal the mass after. However, it doesn't. The individual components after, when we add up all those masses, it's actually heavier than the mass before. And let's look at why this is counterintuitive using a food analogy. So let's say you have a s'more. You have a s'more, and if we decomposed that s'more into its components, like if it fell apart, maybe the marshmallow was not very melted and it fell apart into the graham crackers, marshmallow, and chocolate. So there's actually a discrepancy, or the analogy, this is not the way a real graham cracker s'more would behave, but we have individual masses of the components that don't add up to the s'more when it's all together. So let's keep the numbers simple. Let's say each cracker is 1 gram, the marshmallow is 1 gram, the piece of chocolate is 1 gram. Then you'd expect the s'more, based on the recipe for a s'more, to be 4 grams, but it's not. It's 3 grams. That doesn't seem to make sense because you can't create mass. So this mass difference is called mass defect, and it's part of Einstein's mass energy equivalence. He would say that there's 1 gram of mass that is on the left side of the arrow, but it's here as another form of mass energy. So you have to put in this binding energy on the left side of this equation for it to satisfy a new law called the mass energy, law of conservation of mass energy. So it's a combination of law of conservation of mass and energy. So recall Einstein's famous equation that we've briefly mentioned before, E equals mc squared. And this energy is rest mass energy. We talked about it in the first lesson, talking about all different types of energy. And the total energy that an object has due to mass is this energy. And we talked about that if mass could turn into energy, this is the equation that would be used in order to calculate how much energy. And we said we would come back to it for the nuclear equations, and now we're here. So the s'mores thing was just to provide a visual, but of course the s'more falling apart does not violate the law of conservation of mass. The s'more would be 4 grams. But in the case of the atom, there is this discrepancy. So the binding energy, a form of mass, plus the mass of the atom, a form of energy, is equivalent to that of all the protons and the neutrons at the end, which is not counterintuitive, or which is counterintuitive, can be a bit confusing. So if you ever wanted to calculate this binding energy, you could find the difference in the mass and then sub that mass into E equals mc squared. So through Einstein's new idea that mass and energy are just different forms of each other, there's a new law of conservation. So it's the law of conservation of mass energy. And it says that mass can transform into energy and energy into mass such that the total mass energy in an isolated system remains constant. Often this equation would be used in these questions. So how would we calculate binding energy? We can sum up the masses of all the protons and neutrons that make up an atom, and then subtract from that the mass of the atom. That mass difference, or the mass defect, goes into this mass of E equals mc squared. And recall that c is the speed of light squared. And why speed of light is the magical constant that connects energy and mass it's always been, I guess, interesting to me. So remember, that's 300 million meters per second from grade 10 optics. And make sure you know how to use scientific notation on your calculator in order to get that scientific notation. So a very large amount of energy released in nuclear fission is equivalent to the mass defect. The mass defect is the difference between the calculated mass of an atom based on the nucleons and the electrons present, and the actual atomic mass. And once the mass defect is known, Einstein's equation can be used to calculate the corresponding binding energy. So let's look at chain reactions in nuclear fission. If we have enough nuclear fuel, the products of one reaction may produce further reactions. So a neutron is added to the very heavy atom or isotope. So in this example, it's uranium-235, which is a common nuclear fuel. And recall that from our previous video, the version of an element, the isotope of that element, is indicated by that number after the element name. So U, the symbol for uranium, and then 235, meaning that there's 235 nucleons. So after that first step of the neutron being added, then the nucleus becomes unstable, splits apart into fragments, smaller atoms and neutrons. And then these fast neutrons are slowed down by a process called moderation. And there's some heavy water, which we'll talk about in a second, to help slow it down. And then these slowed down neutrons can interact with these with either more fuel, either more uranium-235, or those fragments, which are still relatively large, causing a chain reaction. So you start this reaction through fast-moving neutrons, and you also produce fast-moving neutrons at the end, which is why it can get out of control, and why, considering the large amount of energy it is released, a lot of control, like you have to obtain tight control of this process for safety reasons. So specifically, so nuclear fission is the reaction in nuclear power plants. And overall, we're taking the nuclear potential energy that is in the nuclear fuel, and we're turning it into energy, electrical energy at the end. Along the way, we're going to be turning the nuclear potential energy into thermal energy, and then into kinetic energy, and then kinetic energy into electricity. But overall, what goes in is nuclear potential energy, and what comes out is electrical energy. And in Canada, we have CANDU reactors, and they are named after their fuel, uranium. So the U at the end is uranium. And then deuterium. So pause right now and test if you remember what deuterium is. So if you remember that it's an isotope of hydrogen, that would be correct. It's hydrogen 2. So regular hydrogen has 1 proton, but deuterium has 2 protons. And instead of using regular water to slow down the fast-moving electrons, we're going to be using, instead of H2O, we're going to replace those hydrogens with deuterium, so it's called D2O. And so since deuterium is so important in this process, as well as obviously uranium, they make it in the name. So CAN for Canada, and then D for deuterium, and then U for uranium. So these reactors use natural uranium as fuel. So we say natural because they are mined. So uranium-235, uranium-238. This generates actually more than 50% of Ontario's electric power. This number is a little bit outdated. And there's been increasing use of nuclear reactors to satisfy Ontario's energy demand because it does not lead to greenhouse gases in our environment. And as I'm hoping you are aware, the climate crisis is a big enough issue that we need to be coming up with we need to be switching to other better options to combat climate change. So taking a closer look at the CANDU reactor, we have the fuel bundles, which is where you would put the uranium fuel. So uranium-235 pellets might be the fuel. Control rods, cadmium rods that control the nuclear reaction rates. We have the moderator, which is heavy water. So because the hydrogen has an extra proton, so each of these 2 hydrogens have an extra proton, the molecular mass of D2O, 1 molecule of D2O would be heavier than H2O. So that's why the nickname is heavy water. The moderator slows down neutrons and absorbs the thermal energy. And then the steam generator, so the steam generator at the top here absorbs thermal energy from heavy water and produces steam. So the nuclear reaction happens here, and then some energy is absorbed by the moderator to help control, and then the products are cycled around this loop, and this pipe is connected to a reservoir of regular water. So in the steam generator, we're taking regular water, and when regular water heats up, if we add enough thermal energy, it will turn into steam. Then the steam flows through to this steam turbine, and the hot pressure, the thermal energy of the steam turns the turbine. So this is where we turn nuclear potential energy into thermal energy. And then this is where we take that thermal energy and we turn it into kinetic energy. Nuclear fission releases energy, which is then converted to thermal energy. So this is just a summary of those energy transformations. And then the pressure given off by the thermal energy, or the steam, runs a turbine, and an electrical energy is produced. Now, the way that this step at the end occurs, we're going to have to put that on pause for Unit 4, Electricity and Magnetism, because in that unit, we're going to learn how a moving magnet will create electricity. But for now, you can think of this as just a magical step at the end that turns steam or kinetic energy from the turbine into electricity. Now, waste is also created in this process, and a lot of consideration goes into how to manage this waste, because it still has there's still radioactive waste and needs to be treated properly and stored properly. Okay, so that's all that you need to know about nuclear fission. I do recommend that you read the textbook section for that. We're going to briefly talk about nuclear fusion, which you'll recall is to join. Fusion needs to join. So, hi class, sorry for that interruption. That is, we have a little robot automatic cat feeder for my cat Fia, and she just got dinner. So, okay, back to nuclear fusion and nuclear fission. So these nuclear reactions occur because these isotopes are not as stable as they could be, and they undergo either fission or fusion so that they reach a more desirable energy state. So nuclear fusion is a nuclear reaction in which the nuclei of two atoms fuse together to form another element. You could think of it as the opposite of nuclear fission. And what causes this process to happen? So nuclear fission occurs with really massive elements. Nuclear fusion occurs in very light elements. So if you look at all the elements of the periodic table, we order them in increasing nuclear mass. The lower the nuclear mass, the more likely fusion occurs. And then after that point, I guess nickel is the point. After that point, anything larger is more likely to have fission. Again, we can quantify this energy using E equals mc squared. So this was binding energy versus nuclear mass. So there's some difficulties with fusion, which is why there's not as much for me to say about it. Fusion requires a great deal of energy. So pause this video and think of why. And I want you to look at this. Oops. I want you to look at this diagram for a hint. Okay, so fusing nuclei must have enough energy to overcome repulsive electrostatic forces. What's in the nuclei? What are in the nuclei? We've got neutrons and protons, but protons, the nucleus is positive of an atom. So why would nuclei want to come together? They are repelling each other because like charges repel. So there would be a lot of energy required to push two positive nuclei together, just like if you had two north ends of a magnet, you would require force to put them together. So you have to have a lot of energy to overcome the force. But where does fusion happen? When there's already a lot of energy available. So stellar fusion occurs within the core of a star. Why is this the perfect storm? We've got temperature is very high in the sun. The sun is one example of a star. So our star, the temperature is very high. Gravity holds particles together. There's a significant number of interactions. In our star, we have atoms that are light. So it checks off all the criteria for fusion. And that's why it's the perfect conditions. So if we wanted to do fusion and harness the energy that comes out of it, we would have to provide really a lot of energy as our starting point. And this could be very expensive, very unsafe, and not very well controlled. So there is research on nuclear fusion, and it has advantages if we could use this, but currently the major power plants in Ontario, OPT, Bruce Power, they're all nuclear fission that I know of. Summary, fission versus fusion. In fission, we have decomposition of a large nucleus into smaller fragments, smaller nuclei. In fusion, it's a nuclear reaction in which the nuclei of two atoms fuse together to form a larger nucleus. Both produce energy. Fission is used in nuclear power reactors such as CANDU because it can be controlled. Fusion is not used to produce power at this moment in Ontario since the reaction is not easily controlled and is expensive to create the needed conditions for a fusion reaction. So now it's time for you to do a few practice questions. Now, rather than being calculation based, you will find these answers in this video and in the textbook reading. So they're more conceptual. And when you complete this video, make sure you submit the exit ticket, the answers to these practice questions. And then after that, I am going to provide optional Unit 3 review since this is the end of the unit. So as much as you can do under the circumstances with the time that you have. And have a great day. Bye.